Over to you, sir. You can start with the session.
Yes. Okay. Thank you, Aditya. I think I'm audible, right?
Yes, sir.
Yes, sir, clearly.
Yes. Okay. I'm sharing my screen, and if it is visible, tell me, please. Is it visible?
Yes, sir.
Okay. Fine. So in the last lecture, we have discussed the experiments in earthquake engineering. Basically, we want to study the effects of earthquake force on lateral load resisting systems, right? And we have discussed this is the philosophy where damage or collapse is not allowed, and we said that there are numbers of structural system we have. So we have a MR frame, we have a braced frame, and we have a structural walls. So we have seen this in the last lecture. This is a basic system, shear wall construction, and this is a dual system. We have some advanced system also for the tall structures. And then we switch over to the need of the earthquake lab, and we said that the earthquake lab is required because the behavior of the structure is uh, quite difficult to assess, because earthquake is a strong is a random strong ground motion, and that is the problem. And we are designing our structure for very small force, so design forces are very low as compared to the earthquake force. And in the last lecture we said that these are the tests we can perform, but as far as this presentation is concerned, we are going to focus on this test. So it will give you the clear idea that how the tests are performed on models, and how can you see the behavior. So main focus is to understand the behavior as far as this presentation is concerned. We are not simulating the condition like a real structure. If a real structure is there, then you have to scale down that particular structure, and you have to establish a relationship between the actual structure and your model. Here we are not doing that. Here we just try to understand uh, uh, how your structure is going to behave if certain types of irregularities you have in your structure, uh, right? So that attempt has been made here. So these are the tests we have we have performed, and we are supposed to see during the presentation. We said that there are the three things we require: shake table, model, and the instrumentation setup. And this is the shake table we discussed in the last lecture. We have different shake tables available, and we said that there are 6 degrees of freedom, right, as far as shake table is concerned. But the uniaxial shake table is sufficient to look at the behavior of the structure under lateral load, right? So we in the last lecture we said that we want to study the effect on structures because of lateral load. And here we are using the uniaxial shake table. So we are putting the model in one direction, and we test it, so we can get the response of the structure in one direction. Then we rotate the model by 90 degree, and again we'll test, so we'll have the response of the same model in another direction. So these are the shake tables available in the laboratory, and we discussed this is the instrumentation setup, and then we said that how the stiffness of the model is derived. This is the way we are deriving the stiffness of the model, and then we said that the free vibration test can be performed, and from the free vibration test we can find out the damping and the frequency of the system, right? So this is the way we can find out damping, and I think we have seen this video in the last lecture. Then we say that the impact hammer test. The impact hammer test means, again, we are disturbing the system by giving the impact, means initial velocity we are applying, and we are testing the model. And by doing this, the structure will vibrate in its natural mode, right? And we can find out the frequency. So this is the impact hammer test. Then we take the case of single story building, and like if it is a masonry building, and if it's a masonry building, single story, the heavy mass is located at the top, and it is supported on the masonry walls, right? So we are knowing that each and every structure should be converted into the mathematical model, right? And then we can we can solve the equation of mathematics. Right. So here you can see this is the structure. This is the single degree of freedom system where the mass is located here. So this is the mass here. It is supported on the column. So this is connected with the spring, which represent the column, and this is the damping, right? So this is the free body diagram, and we have to solve it. And we are knowing that the frequency. Remember, this is very important. You have to understand that the frequency depends on what? Frequency depends on stiffness and the mass, these two parameters. And the stiffness depends on how many parameters? The stiffness depends on so many parameters: the support condition, the elastic property, value of E, moment of inertia, and the height of the structure, right? These are the three things it depends on, right? So we have developed a spring mass model which will represent the single degree of freedom system. And we have from this, we have a variable E, we have a variable I, we have variable L, we have variable M. So these are the four different things we have considered: different material, different height, mass, and thickness. And then we perform the test, right? And when we perform a test, again I'm saying the sensors are placed. Sensor will sense the acceleration, and when we plot a graph of acceleration versus time, time graph we are getting from the vibration analyzer, we are converting into acceleration frequency curve. And in that case, if it is a single degree of freedom, you get a single spike, right? Big spike you have. So this is the corresponding, the displacement what you are getting is the maximum, and it is corresponding to the natural frequency. So this is considered to be the natural frequency of this particular system, right? So we have performed on various things, and I think we have seen this video. I'm not showing it again. So this is a spring mass system with a different mass. This is with variable thickness, and you see we are comparing the manual calculation and with the StatPro results and the vibration analyzer results, right? So we are comparing actually the theoretical values with the software values with the experimental values. And if you are very close to fabricate the model which is actually exist in theory, then results will be very close, right? Now here, this is the point from where we have to start. Is a three means it's a this is a 3-story building. It's a multi-story building, we can say. So we have a heavy mass here, we have heavy mass here, we have a heavy mass of the slab here. So there are 3 masses located, lumped masses, right, at the floor level. So we can say we have prepared a model, very simple model. You can see here the first floor, second floor, and the third floor. That it is supported on a very flexible vertical element, right? Now these are considered to be the column or the wall, right? But here what we are doing, we are not testing this model in this direction. No, we are not going to test this in this direction, because in this direction stiffness is very high. But we are going to test in this direction. Remember, in this direction, this is the direction in which we are going to test it, right? So in the last lecture we said that when we, this is a software model, right? And when we performed the analysis, then you can say this is the mode 1, this is the mode 2, and this is the mode 3, right? These 3 modes we are getting from the software, remember. Why I'm saying this is the first mode? The first mode, you see, from the mode shape itself, you can identify whether it's the first mode, second mode, or third mode. How can you say that? This is the vertical axis, and this is the deformed shape, right? Blue line is a deformed shape, and this is uh, uh, the position of structure in equilibrium, right? Now, when it will deform, how many times a deformed shape intersect with the equilibrium line, right? So it only interact here, right? So it is a single degree of freedom system. In this case, you can see it intersect here, and it will intersect here, right? So this deformed shape is interacting with the the structure in equilibrium at 2 points. So this is the second mode, and here you can see in this deformed shape, this is the one interaction, this is the second interaction, and this is the third one, right? So this is the third mode. So remember, by observing mode shape, you can say whether your structure is vibrating in the first mode, second mode, or third mode, right? Now, always question will arise that what is mode shape? How your structure will vibrate in a different way, right? Always question will arise, because we are knowing that this 3 degree of freedom system is having 3 different frequencies, right? And corresponding to these 3 frequencies, your structure is vibrating, right? You understand? We get the 3 frequencies, and corresponding to these 3 frequencies, your structure is going to respond in a different way. If I'm supplying the lowest frequency, it will vibrate like this. Then it will vibrate like this. You increase the frequency. If I increase the frequency, then again it will vibrate like this. Now we will see that, right? We will see that. So I'm taking, this is the video again. You can see this is very important. You see, this is the again I'm saying this is the ground story. The first story, second story, it is having the 3 masses, right? Now we are shaking in which direction? We are shaking in this direction, right? Now you see what is happening, right? Now I'm applying the very low frequency. Remember, low frequency is applied, which is the fundamental frequency. Now you can see all the masses are moving on one side, right? All the masses are moving on one side. So this is the mode one. Mode one, I'm increasing the frequency. When we increase the frequency, now its deformed shape is changed, right? Now the deformed shape is changed. Remember, uh, this is very important. Are you able to see this video? Hello, are you able to see this video? Yes, yes, okay. Now look at,
But I think it is, yes,
pardon. Yes, yes,
yes, yes, it is visible.
visible now? Okay. Now you can see we are increasing the frequency. When we increase the frequency, its deformed shape is changed. Again, I'm running this. You see, this is uh, uh, the frequency which is applied is very low. This is a very low frequency model, right? So we are applying very low frequency to this model, and you can see all the masses are moving on one side. This is the mode one. When we increase the frequency, now the deformed shape is changed, right? You can see now you apply different frequency to your structure is going to vibrate in a different way, right? Now you can see you increase the frequency, deformation is very less. So here the mass participation is very less in this case, right? So this you can understand from the experiment, right? Again you can see we increase the frequency, its deformed shape is changing, right? Now again we stopped it, and I think so you can understand that what are the mode shapes, right? What are the mode shapes? And this is the picture, right? You can see we have captured the mode one. When the shaking is taken place, it is the 1, 2, 3, and 4. This is a 4-story model, right? all the masses are moving on one side. So this is the mode 1, and you can see this is the second. Now here in this case, what is happening, this mass is moving on this side, this mass is moving on this side, but these two masses are moving on other side, right? So this is very important. So by photograph we are also able to capture this mode shape, right? So you to understand, again I am saying, your structure is going to deform in a different way when you apply different frequency, right? So if it is a 3-story building, we assume there is a 3 degree of freedom system, and we get the 3 mode shapes, and these different mode shapes we can. This is the 4-story building, we will get 4 mode shapes, right, corresponding to 4 different frequencies. Right. So you can see this here. This is the result from the stat flow, and this is the experimental result. They are very close again. These are the frequencies calculated by the experiment, and this is by the software. So they are very close, first mode, second mode, and the third mode, right? Now we are knowing that there are deficiencies in the building. You see, this up to this we have understand the structural dynamics part. This is very important. If you want to understand the structural behavior, you must know the dynamics of structure. And I think this is sufficient. You understand the single degree of freedom system, how your system is going to vibrate. In multi-degree of freedom system, how your system is going to vibrate, right? Now we will see the deficiencies which are present in the system. So deficiencies in the building, we are talking about the open ground story or soft story. We talk about the vertical irregularities, we talk about the stiffness irregularities. We'll see one by one. So the first one is open ground story, right? Open ground story. What is open ground story? Generally the ground floor is utilized for the parking, right? This is utilized for the parking, and therefore we don't find any walls, only columns are present. You can see this column is there, this column is there, column is there, right? And on the upper story you can see there is a column plus wall, column plus wall, because the residential unit or the commercial unit starts from the first story. So ground story is used for the parking. This is known as the open ground story structures, right? You can see this. This is also open ground story. These are the columns. No walls are provided for the parking, and on the first story you have a walls as well as columns. So if you look at the stiffness of the first story is very high, and the ground story the stiffness is very less. Ground floor is very flexible as compared to the upper story. So there is a difference in the stiffness, and in the IS 1893 it is mentioned that the soft story. What is soft story? The soft story is the stiffness of any story is less than the upper story is known as a soft story. Earlier in 2002 code, they have defined a soft story in different way. They said that the stiffness of any story is less than 70% of the above story, it is known as a soft story. But in the new code, they have removed it, and they said that, so how you define the soft story? The soft story means the stiffness of any story is less than the upper story. That's all. It means we are not allowing any sort of stiffness irregularity, right? We are not allowing any sort of soft story, right? This is very important things which is done in the new code. What is the reason? The reason is, you see, in 2001, numbers of multi-story buildings were collapsed, and out of 100 buildings, almost 95 buildings are collapsed because of this soft story, right? Because of this irregularity, right? Again, you can see this is the classical example of the soft story, right? So you have a columns, here, but you have a column plus wall on the upper side. So the upper part, this is a very stiff part, this is very stiff, and this is flexible, right? So the whole structure is actually behaves as a inverted pendulum, right? And you can see this here again it is a cases of open ground story, right? Again you can see this is the new construction which are coming up in Ahmedabad. Again they are following the same mistake. This is something unusual, right? After 21 years, again we are repeating the same mistakes. So we are constructing our houses with the same deficiency. This deficiency was exposed to a great extent in 2001 earthquake, and we are repeating our mistakes. Right? You can see the sometimes. So actually, what happens now? So you can see the upper part, you have a column plus wall. So this part is very stiff, and this part is very flexible. Ground story is very flexible. So what is going to happen when the lateral will come? All the deformation will be concentrated at the ground story. Remember, all the deformation will be concentrated at the ground story. We will see that the whole system will be behaving like an inverted pendulum. Remember, this is the total mass which is working as a total mass resting on this ground story columns, right? So it behaves as an inverted pendulum, and what happens? You can see the what happens during the earthquake. We can see this. These are the classical failures, right? This is from the Turkey. These are the upper stories. Almost nothing has happened, but the ground story was collapsed because of soft story effect. This is the photograph from the Bhuj earthquake. You can see this ground story collapsed, and the upper part will remain as it is. Right? Nothing has happened to upper part. There are damages and everything, but that is because of the ground story collapse. So this is the soft story failure. Remember, this is the soft story failure. You can see this here. What is happening? The glass panels are provided, and only columns are here. On the upper side, you have a wall plus column. So upper part is stiff, lower part is again a flexible, and the failure had been observed, right? Again, you can see the soft story failure, the ground story collapsed, right? Ground story collapsed. Upper part has not observed significant damage. This damage because the ground story columns are collapsed, and that's why the upper part has observed the damage, right? This is the most classical picture of 2001 Bhuj earthquake, right? Again, soft story failure. At the same time, the torsional effect comes in picture. Torsion effect, right? And torsion plus soft story both have taken place, and this is going to happen in 2001 Bhuj earthquake. Right. So we have prepared a model. We want to understand what is the soft story effect, right? So what we do, we are preparing a model in such a way that the shear walls are not present at the ground floor. All right. If we prepare this model, then definitely it will exhibit the soft story, right? Now we can see again the video, so you can understand this. This is very important. Just wait for a moment. I have to make certain corrections. Okay, now you can see here on the upper story we are putting the shear walls. These are the steel plates. There are columns throughout, right? It is a columns throughout, plus on the first story and second story we are placing the shear wall, but on the ground story we are not placing the shear wall. So there is a stiffness difference. The stiffness of the ground story is less as compared to the first story. But the stiffness of the first story and stiffness of the second story, there is no difference. So you don't have the soft story there. So you have a soft story at the ground story level. That's all, right? Then we'll see how your structure is going to behave. Remember, this is very important. These are our ME students who are performing this test, and I think they try to understand soft story effect. Okay? Just look at the behavior, right? If you see this, you will find that the most of the deformation, upper part is behaving like a rigid body, and a lower part is basically having the most of the deformation, right? Most of the deformation is at the lower story, right? Upper part is deforming like a rigid body, right? You can understand this now, right? Again, I'm repeating because this is very important. You have to understand this effect. Again, I'm repeating. Just go through it. You see, vibration is started, frequency is low, we are increasing the frequency, and look at the behavior. The upper two-story, they have shear walls, and therefore they behave like a rigid, and the total deformation is concentrated at the ground story. Right now, you can see. Fine. So total deformation is concentrated, and we are knowing that our structures is having a limited deformability, and therefore uh, we have to look at this effect very seriously. Now I will show you the soft story failure, right? And I think that will tell you everything. Again, I have to change the orientation. Now look at this, right? I'm applying the ground motion, right? Again, the same model is there. We are uh, uh, also placing the uh, level indicator. So we assume that the floor is horizontal, and now we apply the earthquake motion. Now look at this. The total deformation is concentrated at the ground story, right? Upper stories are deforming like a rigid body. So no deformation on the upper story, but the most of the deformation is concentrated at the ground story. Now you can see what happened. It breaks, right? It breaks. And now you can see also the students are clapping, right? They have smile on their face. In reality, when structure fails, we become sad. But in the laboratory, when model fails, we learn a lot, right? And here you can see uh, the structure fails, and because of lot of uh, 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 reverse reversal of stresses, um, here the member failed and a lot of energy was released. So you can also feel heat there, right? So I think one of the participant is here, Yogesh Chavan. Yeah, he has witnessed this soft story failure. uh, we can see once again look at carefully. The ground story is a soft story, the, and the upper story are deforming like a rigid body. And the most of the deformation is concentrated at the ground story. Now this is happening when you are creating soft story in real structure. Now vibration continues, and what happened? What happened? Deformation. Yeah. After so many cycles, because of the reversal of the stresses, it fails. Right? And lot of energy release. So you can feel a heat there. So this structure is not able to absorb the energy supplied to this structure, right? So this is known as a soft story failure. Soft story failure or open ground story failure. So once you will see this, you will never forget. I tell you, you will never forget such kind of failures. So in reality, when you see such kind of pictures, then this kind of uh, uh, film should come in your mind that okay, this structure is going to behave like this under earthquake, right? So when you are when I'm visiting any structure, or if I'm visiting mall even, then first thing we come in the mind is the irregularity. Which type of irregularity this mall is having, and what will happen if earthquake is taken place, right? So this is the soft story failure. Now this is very interesting, right? Now we have placed the sensors also. So this will tell you the what are the accelerations, right? So the acceleration is this is at the base and this is at the ground story. But the important thing is displacement, right? What is the total displacement? Total displacement is 40. Total displacement is 40. Out of 40, almost 30 is at the ground story. You understand? So actually on the ground story, if I say the 40 is there, then almost distribution will be 40, 14, 14 or 13, 13, 13 at each story. Then a uniform distribution of the stresses will be there. But here what is happening? Out of 40, total deformation at the ground story is 30. It means a lot of stresses are concentrated at the ground story, right? 75% displacements are observed at the ground story out of total displacement at the top, right? So total displacement is 40, and out of the 40, 30 is at the ground story. So your columns at the ground story are heavily stressed, and therefore the failure is observed, right? This soft story may be taken place at any particular place, right? Any particular place. You see, you have to relate this the masonry structures. These are going to happen with the masonry structures even, right? So uh, sometimes we have a soft story at upper story. For example, this is the classical case where you can see this is the upper story where the columns have been removed because they want the auditorium, and therefore uh, the middle story becomes soft, and the failure had been observed at the middle story, right? You can see this, right? This is the case where the failure taken place and because of the soft story, right? uh, when we are putting this our shear wall in a unsymmetrical way, right? So then what is going to happen? We are always saying that your shear wall should be placed in a symmetrical way, right? Why we are saying this, you can understand from this. When the structure is unsymmetrical, torsion is going to induce in your structure, and I think we can see this here. You can see the shear walls are placed on only one side, only this side. There is no shear wall on the other side, right? So this part is very stiff, this other part is very flexible. So this flexible part will move more, the stiff part will move less. Then what will happen? We will see this. Look at the behavior. The torsion comes in picture. Torsion comes in picture, right? Okay. So you can understand, because of the unsymmetrical shear walls, uh, earthquake force is there. In addition to earthquake force, you have additional torsion, right? So I'm always saying that it is very difficult to deal with the earthquake force, and you are introducing the torsion, so you are making your life more miserable. Okay. uh, so these are the results of acceleration versus time. We are getting this result, right? Because of now what is the important thing? Now the important thing is that uh, if we are vibrating our structure in a uniaxial direction, so we must have acceleration in one direction. But here what is happening? If you look at this, you have the acceleration. This is in x direction, this is in the z direction. So we are getting acceleration in both the direction because there is a torsion. There is a torsion. right? So in the principal direction, in x direction, you are getting the higher acceleration, and in the other direction, you are getting the less, right? So you have to understand that if you are introducing torsion in your structure, then your structure is going to have a acceleration in both the directions, right? Now the another important thing which Shetala ma'am has addressed, that when the two buildings are very close to each other, when they are very close to each other, then uh, uh, for the dead load and live load, they behave properly. But when the lateral load comes, then these two structures will vibrate in a different way, right? And if the sufficient gap is not provided, then they will hit each other. When they will hit each other, that is known as a pounding. That is known as a pounding, right? So we are knowing that this is a low rise, this is having maybe a high rise. So the frequency of both the buildings are different. Both the buildings are different, right? So what is going to happen? And here, this slab will hit this particular column, right? This slab is hitting the column. Now, if we have designed both the structures correctly from earthquake point of view, even though if this slab will hit the column, we have not designed this column for this impact force, and your structure may fail because of this impact, right? If the column is failing, this column may lead to the collapse of the whole structure. Remember, this is very important, right? Now here you can see these two structures are very close, and because of the pounding, you see a lot of damage. Right here, these two structures, because of the pounding, this building collapsed. What is the reason? The reason is, out of these two buildings, this building is weaker, right? And definitely the weak building will collapse. You can see this again, pounding at the top, right? So you see a lot of damage here, right? This is again a pounding. Right? These buildings are very close to each other, and pounding has been observed. So we prepare a model of pounding. So without pounding, pounding of slab with the column, pounding of slab with the slab, right? We'll see that. So here, the models are created in such a way that both is having the different frequency, right? So here, this slab is hitting the column, and in this case, the slab will hit the slab, right? So what is needed? You must have a sufficient gap in between these two these two buildings, right? So first we'll take the case of pounding when slab to column, right? Now again, you can see this, that here this is a two-story building, and the white one is a single-story building, right? So frequency of both structures are different. If frequency of both structures are same, then they will vibrate in a single direction when the harmonic motion is applied. But here the frequency of both the buildings are different, and generally when we construct in a real sense, the frequency of both the structures are different. So this is a single story building, this is a two-story building, and what is going to happen, you can see here, right? You see, we apply the same frequency to both the structures, but the first one, the white structure is start vibrating. Now when the frequency is increased, the second structure start vibrating, and what you can see is, you see both the slabs are hitting column of other structures. Now look at this, right? This slab is hitting the column, right? And we are knowing when the impact is taken place, the value of load will be twice as compared to the gradually applied load, right? We can see the pounding of slab to slab when uh, okay, you can see now the slab to slab pounding. Again, the frequency, one is a single story, another is a two-story building. When slab is hitting the slab, a lot of energy will be imparted, I tell you, right? But out of these two cases, slab is hitting the column and slab is hitting the slab. The slab hitting the column is the worst case scenario because we haven't designed. Here, there's definite impact is there, but this impact is going to transfer to all the four columns, right? While in the earlier case, when the impact taken place, it is transferred to only two columns. So slab to slab pounding and slab to column pounding, out of these two, slab to column pounding is worst, right? Now you can see this is a without pounding result, right? Now these are the peak accelerations and the displacement in case of slab to column pounding, and you can see the additional force, this much force, it is almost more than the value of weight of the slab. It is transferred in original direction in form of an impact force, right? So this impact is really very dangerous, right? And here from the record you can see this will tell you the impact, right? There's a sudden increase in the force. These are the this many times the impact is taken place, right? Here these are the impact taken place. Okay, so this you can see when the pounding of slab to slab, right? And here the important thing is again the amount of force which is transferred is little less as compared to the first one, right? So what is the solution? The solution is you have to go for separation of these two buildings. You have to provide a proper gap. So you have to assume that these two buildings are vibrating in opposite direction, right? So you can calculate the deformation of building 1, you can calculate deformation of building 2, right? And once you calculate this, the code is saying that the drift is 0.4%. So you can have this 0.4% multiply by R, response reduction factor. This should be the maximum gap you have to provide to avoid pounding, right? So you can see this here, the pounding is taken place. If the gap is there, there is no pounding. Then the another irregularities we have, that is a L-shaped building, C-shaped building, or S-shaped building. We are saying that such kind of buildings are not performing well. Now what is the reason behind it? The reason behind this is this may not be symmetrical about a point, and because of the irregularity in the shape, the certain portion of your structure will get higher stress. We'll see that. So first of all, we'll see actually which type of structures we are talking about. This is the double C type, right? Or you can say E type building you have, right? You can see this is a building L type, and in case of L type, this corner is more vulnerable. What is the reason? The reason is when the shaking is taken place in this direction, then this portion and this portion will move in a different way. If it will move in a different way, then this corner is at a high risk. Right? So this is known as a re-entrant corner. Re-entrant corner, and this re-entrant corner always highly stressed during the earthquake. This is again a C type of building you have, and again this corner is always critical. This corner become a very critical, right, from top to bottom. This and this. You might be knowing that we have two 10-story building collapsed in Ahmedabad, Sikhar and Mansi, and one of the reason of the collapse of the Sikhar is this. It was a C type of building, and because of the C shape, the re-entrant corner, the corner is highly stressed, and one portion of that C type building collapsed. Right. Again, you see such kind of structures in metro cities. Right. You can see such kind of structures in the metro city. Now, what I told you is this. This is the Sikhar building. Now, it is a C type building, and the the portion on this side, it was collapsed, right? And so when you construct such kind of building, you have to take enough care where uh, the the two portion of a building meets at this particular point is not a re-entrant corner, right? So you have to be very careful. Remember, very careful. You have to design those elements for the higher stresses. Look at this. Right? Now, this is a classical picture. Most of the time, architect is saying that I want a front part. This is the front part. I want good elevation, and for good elevation, you cannot place your lift well in the front. You can place it on the back side. So you are placing on the back side. What is happening? This is made up of steel, and this is RCC. So this is very flexible, while this is very stiff. So this portion will move more. Remember, this portion will move more, and this is less. So it is like it will undergo the twisting like this, right? So the slab will rotate. When the slab will rotate, the torsion will column will undergo torsion, right? So this is happening here. You can see this. When the shear wall is placed like this, this is the shear wall, right? And then the whole building will rotate like this, right? Or it will rotate like this in the other direction. So torsion in the column or shear wall or in the vertical element is going to be observed, right? So there is a what is happening in this case. You can understand here. Uh, Here, the center of stiffness is moving on this side, right? This is the center of mass. So there is a clear gap between the center of stiffness and center of mass. And then what will happen? The rotation of the slab, and it induces torsion in the column, right? So this is the torsion in your structure, right? And so many failures have been observed. You can see this because of the irregularity, right? These are the classical example from the 1995 Kobe, Japan earthquake. Here you can see they have a columns on the front side. They have a shear wall on the back side. So this the front part undergo large deformation and it collapsed. So we prepare a very again simple model. We just want to understand. We want to visualize how torsion is going to come in picture, right? So we will see this. So we prepare a model in such a way that this is the L-shaped building, L-shape like this, and then so we prepare two different different models. They are regular in nature, and then we connect here. We connect these two here, right? When we connect, it will become a L building, L type building, right? And if it become L, then what is going to happen? Simple. Look at this. We have created two separate models, 1 and 2, right? Now, if you look at these two models, then you find that that and the white is having 4 columns, while the orange is having 6 columns, right? So if we shake it in this direction, right? If we shake it in this direction, then this is very stiff. That means orange is stiffer than this white model, right? So they will actually observe different deformations in lateral direction, right? So in that case, this corner will observe differential movement, and they are highly stressed, right? So we will see that. So this is the test we performed, and we get the record of acceleration versus time, and I am showing the video. So we are not going in detail as far as the results are concerned, because it will take a lot of time. But look at the result. Look at the video. Right? Just look at this. So they are connected here. Both are connected here. So we have provided a connector, and then we apply the force. Again, one of the participant, Yogesh Chavan, is sitting there. You see, it is placed with the all sensors. We are measuring acceleration, and now you can see the torsion in the building, because both the models are having different frequencies, and we apply the same frequency. Both will behave in a different way. So this is known as a this is a torsion we have, right? And these are the results we get: peak acceleration, displacements, right? Uh, but you see, this is very important. When we are connecting this, when we are connecting both the models, then what is happening? We get the acceleration in x direction. We get the acceleration in x direction. We get the acceleration in z direction. Why? Because the torsion is induced. When the torsion is induced, then you get the acceleration in both the directions, right? So the x is the principal direction, so you get the higher acceleration in this direction, and another direction, horizontal direction, z, is the not a main direction, so you get a lesser acceleration in this direction, right? Then we have a liquefaction model. We are studying the liquefaction also, and uh, in the liquefaction model, we take the different types of soil. Like we are knowing. Do you know what is liquefaction? What is liquefaction? Can anyone tell me what is liquefaction? What is liquefaction? Just to break the monotony, I am asking question. What do you mean by liquefaction? I want to answer from you. Anyone? Yes, anyone? Am I audible?
Yes, sir. So shall I?
Yeah, sure.
Sir, it is the condition of sand when it has a very low density, right? So when we apply force, the sand starts to slip away. So it becomes very sort of liquid in a way. Its behavior is
Not the
same as a
correct.
liquid.
You are very close, but you are not the correct answer. You want to add anything? Anyone else? Anyone else?
Sir, can I?
Yes, please. Please.
Sir, under the influence of lateral force,
Yes.
the soil loses its shear strength. Hence,
Yes.
it behaves as a liquid that is known as liquefaction of soil.
That is correct. It loses its CS. Why it loses its CS strength? What is the reason?
Sir,
What is the
sometimes
reason?
the sudden change in the stress condition.
Agree, but again,
But sometimes the solid behave like a liquid.
okay, but still, what is happening? I want to understand that phenomena of liquefaction. I want to understand that. Okay. And anyone else want to answer, please?
Yes, sir. Hello.
Yes, please.
Sir, when when soil loses its shear strength due to lateral pressure and due to pore water pressure, which is acting in upward direction. So when tau
Yes.
minus that is sigma minus u. So now if the effective stress is an, zero due to upward water pressure, that is the phenomena of liquefaction.
Okay. Fine. Still, I want one more thing to add. If anyone can add that part, please. Yes, Yogesh. Yes, Yogesh.
In case of cohesionless saturated soil under vibration, the soil loses its shear strength and behaves as a fluid. So
Yes, that is correct.
cohesionless, saturation, and vibration. These three things are required, are means essential for liquefaction to happen.
Yeah, it's perfectly right, Yogesh. You have described the condition properly. A very simple way to define liquefaction is that you see, when we are talking about the soil is getting strength from two aspects. One is cohesion, another is friction, right? So the strength depends on C and phi, right? So when I'm talking about the cohesion-less soil means sandy soil I'm talking about. If it is cohesion-less soil, then C is 0. So no cohesion. So the strength of this soil depends on only friction, right? Friction. So I'm talking about the cohesion-less soil, right? So if the foundation of any structure is on cohesion-less soil, right, and if the water table is high, when the shaking taken place, this water will come up. When this water will come up, then the space between the sand particle is filled up with the water. When the space between the sand particle is filled up with the water, then friction is lost. So in cohesionless, there is no cohesion, and now there is no friction because of the additional water between the soil particles. So no cohesion, no friction. So what happened? The soil will behave like a liquid. Soil loses all its shear strength, right? Soil loses all its shear strength, and because of this, it behaves like a liquid. And we are knowing that if you try to walk on a liquid, what will happen? You cannot walk because liquid don't have the shear strength. The same way, when your structure is founded on such kind of soil, right, and liquefaction is taken place, then your structure is on a liquid. It's on a material which is having a zero shear strength. So your soil is not able to support your structure, and it will uh, uh, get differential settlement, or it can rotate, right? So that is known as a liquefaction, right? We will see that, right? So that is liquefaction. So this is the way. Again, I'm saying cohesion-less soil, that is to be required. Second part is you need a higher water table, and the third is the vibration. These three things are the necessary condition for the liquefaction, right? So soil will lose all its shear strength because of the increased pore pressure, and then your structure may rotate like this, right? So we have create the conditions I think okay. Just for a moment.